Yeah, so I'll be following on from Vitali, who nicely introduced the concepts of our invariants. I'm going to do a little recap of that, reintroduce some of our definitions, and then at the end we'll hopefully get to see some nice plots of this crystal universe as mapped by our invariants. So just to reintroduce our motivations and requirements for our crystal descriptor, just this one slide. So what we're looking at here is this top box should represent containing all periodic crystal structures, infinite periodic crystal structures. I've represented them by these finite simpler objects. And we have a few conditions on what we want to happen with this map. So Vitali ended with mentioning this map. This top box containing all periodic structures is a little difficult to work with. So the way we resolve this is with a map, which has a few conditions attached to it. So the first one, you can see these objects within this blob here are all related by an isometry, rotation, translation, reflection, and those don't affect the structure of the crystal. Well, I'm aware that reflections do, but for these purposes, it's an isometry invariant to keep things a bit simpler. Now, identifying if two things are isometric is not necessarily easy, so a good way to do it is with an invariant. So what we're seeing here is in this map I've called I for invariant. All these things which are equivalent to each other with an isometry are mapping to the same place in the output at the bottom. So what we're trying to do is take these crystals and map them to a simpler mathematical space. One of the rules is if I apply an isometry to a crystal and map it, then it shouldn't change the output. Okay, so sort of the inverse to that is called completeness, this condition over here, that if I have something genuinely different, we want it to map to a different place, unlike something like density, which may not always have that property. And finally, we want it to be continuous, so hence continuous isometry invariant, meaning a gradual perturbation shift in the atoms, even if it breaks symmetry or you change the unit cell, should always result in a smooth path in the output space. So let's reintroduce this definition, pointwise distance distribution. This is the invariant that gives birth to all the other invariants we'll see. So quite simply, we take a crystal, look at the atoms in the motif, and list distances to the neighboring atoms around them in order. So this doesn't stop at the boundary of the unit cell or anything. You could choose infinitely many neighbors, but we have to stop at some point, at least in our computer, and we call that stopping point K. So here I've chosen four numbers, but we could keep going. Do this for every atom in the motif, and we have these distance lists. Collect them into this matrix, and we put a weight on the row of each of on each of these rows, representing the frequency, if you like, of that atom in the motif. If you're a crystallographer, you see that that's basically equivalent to Wyckoff multiplicity. So you can do it that way, but in this case, we've just got quite simply four unique, distinct environments of atoms. So after this, if we have identical rows, we collapse them. That's usually because of symmetry, although not always, I suppose. And after that, simply apply a stable ordering to this matrix and reorder the rows. And we've represented our crystal with this matrix. This is our invariant, and it satisfies, very close to satisfying every condition that I outlined earlier. It's pretty much perfect, except for very, very small subset of things you have to construct in order to confuse the completeness condition. But regardless, if you're, I won't be able to introduce some of our secret sauce. So these things are compared with something called Earth mover's distance. Obviously, a different crystal could have different number of rows here. If you break symmetry, we could have a different number of rows. That's all just resolved by our comparison. But I'm not going to be able to talk too much about that. I should move on. But each crystal gets represented by this matrix, and we can compare these matrices. However, our plots don't use this matrix because it's kind of difficult to plot that matrix. So we could take this average. Vitali introduced this first, but you can obtain it through taking an average over the columns of this PDD to get one vector. So this vector is now the thing representing our crystal, and it's kind of like the average distances to nearest neighbors across all of motif points in the unit cell. And these numbers are obviously increasing as neighbors get further and further away. This is a little bit weaker than this whole matrix because we've destroyed some of the information, but it's still very distinguishing. There are actually no examples that we could find in the wild of real crystals that where there's a coincidence where they are different crystals, but they have the same AMD. So this is something that's easy to plot and is much, much, much faster than comparing with the PDD. So you can compare everything in the CSD in well under an hour with just this. If we have a question, I don't mind taking a question now, but if not, I'll continue. Okay, so this AMD obviously is increasing, and I should introduce this, where we kind of normalize it to make it make a bit more sense. So if you're familiar with the density function, you have a time you divide by, because when you expand like a sphere, the radius of a sphere, it gets bigger. So you want the proportion. Now this complicated term next to AMD is its asymptote, or it's what it approaches. So this AMD just keeps increasing and increasing. It will eventually approach this complicated term that I've subtracted from it here, and we've given it a new name, ADA, ADA. And you can see what it results in is this kind of sound wave type looking thing. This is what's representing our crystal. And I like this example because we can see crystals which are pretty similar in a kind of in a fashion that's, I'm sure, obvious to a human, but they use different molecules, and the sound wave shows you that they are being represented sort of similarly in this output crystal space. Okay, so this is what we're looking at with the representation of our crystal. When I come to plot our crystal space in just a moment, we're going to be taking just a few values from the x-axis here. So we're essentially taking like a vertical slice on this plot, just in 2 or 3 places, which is of course quite a low dimensional projection, but it tends to reveal quite interesting things anyway. And full comparisons involve this full sound wave, but we're only going to look at 3 pieces of it. And I should mention as well, because it will be relevant, that you can subtract this asymptote from the AMD and get this, what I've plotted. You can also divide by the asymptote. And what that does is makes uniform scaling. It makes the uniform scaling of a crystal not affect the output. So with this ADA I've defined, 2 things which are equivalent up to uniform scaling will be different. We'll be able to see that. But when you divide, they become seen as the same. So you can choose which one you prefer. Now, with that, I've introduced what I need to. I'm going to start this demo. So I'm going to try and go a bit more slowly than usual because so I don't confuse people. So let's have a look at some pieces of the crystal universe. I'm going to start with the ICSD, and I want to look at, well, first of all, I don't want distorted structures, and I would like to see only cubic, crystal system, cubic. I'm going to do a 3D scatter plot. Now I choose 3 values of K. I could choose a lot of values of K, but I've chosen some decent-ish values for this presentation. You want to choose them somewhat far apart because some of the values are correlated. We want to see a maximum information. I'll color this scatter plot by this space group of the crystal. They'll all be cubic, but there's various space groups in there. And then just a couple of style things, and let's plot that. Okay. So what are we looking at here? This is the space of cubic crystals in the ICSD, as plotted by our invariants. And we can obviously see some interesting sort of pieces or artifacts appearing, which we're going to explain. So first of all, the most noticeable thing is the big lines pointing towards the origin. these are very perfect. You can see if I sort of pan around them, they point exactly towards the origin, and these can be explained mathematically. They come out of they 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 can be proven to exist essentially just via the mathematics, the construction of our invariant, because we're careful about our rules. And what these are is uniform scaling. So I mentioned uniform scaling. We are not dividing by the asymptote yet. We'll do that in a minute. But one of these lines, if I go up to it, like this one over here, let's see what's on the line. So I can actually open up the structure on the right here. Right, so this is what we're looking at. So this is what diamond looks like, except the atoms are all carbon, right? And everything on this line will look exactly like this. I could just pick another one. And if I hover over this, if you have a look at ABC there, the side lengths of the unit cell, that's the fifth line down. I'm going to move the cursor up the line. You can see that the cell parameters gradually change as I move up the line. So this line corresponds to uniform scaling. And all the other lines are similar. They all correspond to uniform scaling, but they're all different structures. So if I pick one from over here, we're looking at face-centered cubics. And I'll briefly point out, because I have them here, so where my mouse is hovering is where these various things are. This stuff is a simple cubic. I just showed you a face-centered cubic. There's BCC structures over here. I think this line is a bunch of perovskites, and we saw the diamond-like structures over there. Now, one last thing on this plot. So, actually, I will go over here to a simple cubic, I think. No, I will stick over here. So, this is our diamond line, and you can see these orange points sort of trailing off of the line in a almost like a smooth. It's been kicked off the line, right, just by a small perturbation. So let's look at this. Let's look at this, because this is really the crux of our invariants. If I look at this, yeah, that's exactly what the diamond structure would look like if it was all carbon. And then this has twice as big a unit cell. Almost like it's just been extended, but it's off the line. If you were to literally just double this unit cell, it should remain on the line because the structure has not changed. But if I zoom in here, I'll view it exactly along the a-axis, move it in. Hopefully I can see here somewhere. Maybe it's a little difficult to see. Oh, there we go. I found one there. So I should not be able to see the atom behind it if the symmetry was perfect. But what's happened is the unit cell was doubled, and then one of the atoms was moved just a little bit. So that meant that the structure is slightly off the line. But even though the symmetry has changed, this might be considered different space group or something. It's realized as a smooth change, a small change in this output space here. Yes, I believe I'll leave that there. What's interesting is if you fly around this, there should be only cubic crystals. I've designated what they are, cubic, what space group they are. I chose to use PyMapGen's symmetry analyzer with the default settings because what else am I? That is probably the thing that most people would agree is going to give you the right answer, although some people will disagree. And this is kind of the point, right? If I change those parameters, I'll be labeling some of these crystals as not cubic, or I'll be labeling some other crystals as cubic, and that's a discontinuity when we. So some of these lines where this all should be cubic crystals, where the three unit cell lengths are identical. There are some where they're just a little bit off, so it shouldn't be cubic, but the symmetry analyzer says it's cubic because there's tolerances. Well, if I keep deforming that structure and I keep changing the cell lengths, at some point the symmetry analyzer is going to tell me, oh, you're not cubic anymore. But it was the whole time it was one smooth deformation, and that's realized in this space. So with that, let's look at something else. Now what we're going to do is introduce what I mentioned about uniform scaling. So now I want to divide by the asymptote, and what that's going to do is all these lines are going to be disappearing and they're going to be replaced by a single point because uniform scaling doesn't affect the output invariant. They'll all be sitting in the same place. So let me just change this. Hopefully it's okay. Yeah. So now plot's changed quite a bit and all those lines towards the origin have disappeared and they've been replaced by hot points. So right here is where all the diamond stuff lives, and we can show that. I can highlight this little dot here and bring them all up, right? And I could just scroll through these. They all look like this. 1,700 items sit all there, which is why it's quite a hot spot. So everything, if you uniformly scale a crystal, it won't move in this plot. Now I want to look at one particular fun artifact, which I quite like, and it's this line over here, this white line. So I could replot this with just space group 227, which is what I know these are, but I think hopefully everyone can see this white line that has very strange regular spacings of the points. We have like these very hot points, which are very evenly spaced, and then in between them we have some not quite so hot points. And I'll show you how I sort of guessed what this was. If I zoom in, I'm just going to count the number of points between two of the hotter spots. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is a very popular number with humans because we write everything in base 10. And what we're looking at is decimal places that are written down in fractional coordinates in a CIF. So I'll actually click on one of these so you know what it is. This is a particular kind of, is it a spinel? Yeah, I think this is a specific kind of spinel or inverse spinel. And it depends on only one geometric parameter. So this is not uniform scaling, it's one atom or multiple, but they're moving and there's only one parameter you can change. They call it epsilon, and it can range from 0, which would be right over here, I think. And as you increase it, it moves along these lines. And because most CIFs write things down to 3 decimal places, that's the really hot ones you see in between. The ones that write them down to 4 decimal places are the less hot ones in between those. And it's nice artifacts like this that appear sort of all over the map. And there's a few other things sort of like that, but I'll leave this particular interesting artifact just for now. Okay, I think I have some time, so what I'll do is quickly show the whole ICSD like this as a kind of heat map. So you can see there's a lot of stuff in the ICSD and it's a bit of a blur, which is why I showed just cubic crystals, but really, really popular stuff stands out. And an analogy we often use in presentation and such is stars in the universe. And I like this because they actually do pop out just like that. So you can sort of wander around this space and see what's there. But I'd like to move on to maybe something more specific. So I think what we'll do is, yeah, I'll show carbon allotropes first. Let's hope this works because it can be a bit temperamental with some of these things. I apologize. It won't take too long to get back if that's the case. We're going to use the normalize. So we're now dividing by the asymptote. So uniform scaling doesn't matter. And what I'll also do, let's first of all try updating this. I'm a bit worried that the program will crash because it has done that before, but hopefully it won't. So a little hard to see, I would say. This should be carbon allotropes only. Diamond lives over here. I've already shown where that lives, and there are a bunch of others. If we wanted to, we can use another plot, and I'll plot a little dendrogram. So now we're going to use the full invariant, which should contain a lot more information. It's kind of hard to separate things on the right here. Ah, there we go. I can reopen this quite quickly. I knew specifically something like this is a little temperamental, but it's okay. In fact, I think I will show something like calcium carbonate instead. Hopefully this will be okay now. Let's plot the CSD with calcium carbonate only. And in fact, I'll just leave, I'll color by space group, but then I want a dendrogram, and hopefully it'll be okay this time. Yeah, there we go. So the crystallographers probably know better than me how many polymorphs of calcium carbonate they are, but they're very well separated. And this plot here, if I hover over a particular cluster on the right, then it highlights the equivalent thing on the left. So you can use these things kind of in tandem to distinguish between different things. Or alternatively, I can just change this up. So I'll mention that if you have a favorite crystal or a favorite composition or a favorite CSD rep code family, we can try plotting it. One I know is quite popular is glycine, so let's try plotting that. Okay, so we have a lot of points here. I wouldn't say necessarily that well separated, but they are kind of separated. One thing that we can do, however, because our invariants are designed for any periodic structure, we can collapse a whole molecule down into a single point at its center of mass. And that is often very effective at capturing what we want. So let me just quickly replot this with that. And we can see now that this space has some very well defined clusters, and on the right it clusters as well. I see I'm running a bit out of time, so I'll just mention that this also serves as an interface to compare our crystal structures. So I could just do this right now. Vitali mentioned the ALAB paper. So we looked for the ALAB crystals in the ICSD and we found them. I mean, I've just repeated the experiment within like 5 seconds right here. It usually takes a while to search an entire database, but vectors are very fast. And you look through these and you can find the equivalent crystals. That's how we did it. It takes very little time at all. So yeah, that's been the geomap and our invariants fast comparisons of crystals. If you have any crystal you want to search for in a database, please email us and we'll help you find it.
Thank you very much, Daniel. Very nice demonstration there.